Ok, bonjour. Merci d'être venu. Welcome. Thank you for coming. Okay. So, just to sum up where we are. So we started by looking at what can be measured. So a linear response and fluctuation. And then we focused more recently on the Green's function, so spectral weight of the single particle and self-energy. Now in the next 2 weeks, we're going to work on the Coulomb gas, which is a specific model where we will compute these quantities. So what do I mean by Coulomb gas? I mean a model that's called Gelium. So we assume that we have a background, a positive background that makes the system neutral, but it's not moving. We will introduce the motion of the background, in other words, phonons at a later time. But this is a very simple model, which is where you have the complete translational invariance. No lattice, no nothing. But it will allow us to find some very important physics. For example, the physics of screening. Why is it that the Coulomb interaction is in a many-body system is screened so that it looks like short range at low frequencies? So that's a way to, it will be important to justify a model that we will use later, the Hubbard model. So then for this Coulomb gas, we will also compute the self-energy. And we will find that simple approximation, mean field approximation, this is the R3-Fock approximation, gives a ridiculous result, like an effective mass that is 0 at the Fermi level. So we will see how to correct that using what we will have found for screening. And it will lead us to something that's called the GW approximation, which is widely used in electronic structure calculation. So, so it's based on the fact that the charge fluctuations that come in the calculation of the susceptibility, as you will see in a moment, these charge fluctuations can be treated within RPA, and that's what's called random phase approximation. So we will also see what this random phase approximation is. Okay, so unfortunately, I still need to do a little bit more formalism. But why? Because we want to do perturbation theory to compute this. It's too difficult. I mean, there's no other way because kinetic energy and potential energy don't commute, so we need to do something. So I will introduce a method based on functional derivatives, based on source fields. So we will extend, in other words, our problem by adding some field that's completely artificial, but would allow us to derive a lot of useful relations. And at the end, we will put that field equal to 0. So in mathematics, we do that often, right? I mean, to do integrals on the real axis, it's often useful to introduce complex numbers, right? We've seen that already several times. And even though our Hamiltonian always conserves particle, introducing creation and annihilation operators, the annihilation operator goes from a space of n particle to a space of n-1 particle. So we enlarge the space of, that we are looking at. Instead of looking at just n particles, we look at n-1 and +1, etc. But doing that, we said that we also simplify the problem. In the case of the field operators, the space where we combine, systems with 0 particle, 1 particle, 2 particles, etc., is called Fock space. I forgot to mention that at that time. So I will introduce these method source fields in the classical context, and then we will, in this section, we'll go in the quantum case. And in 3, I will give you a sort of impressionistic view of what we will do more carefully later. So in other words, it will be a cartoon that will allow us to see why we do these things. Yeah, to So that's the plan. So are there any questions? Okay. So source fields, I start with the classical case. So let's compute the partition function in the presence of a magnetic field. So that will be equal to a trace e to the minus beta k. So k is h minus mu n minus hm. Okay. So you see that now if I take the derivative with respect to h of the log of zh, okay, it's the log, so I get 1 over this, trace e to the minus beta k minus hm, and in the numerator I get the derivative of this. So if I put a beta here, what I'm left with here is a trace of e to the minus beta k minus hm times m. Okay. So what is this? This is the expectation value of the magnetization in the presence of a field H. Now suppose I want to compute the mean square or the fluctuations, if you want. Then I will do d square log zh dh square beta square. So I get a term that comes from taking the derivative of the numerator. Okay, so the derivative of the numerator will give me m square here. So I will have the expectation of m square. But the magnetic field is there also. Okay. So when I take the derivative of the denominator, I get minus 1 over z square of h. Okay. So this is 1 over z. So I get minus 1 over z square. Then I do the derivative of the denominator. So I will get what? I will get this square, right? I will get the trace e to the minus beta k minus hm times m, everything squared. Okay. So what is this? This is m square h minus m square. So it's the variance. And if you remember, this is the generating function for cumulants. So we call this also the connected function. Connected because we sort of subtract the trivial part. In terms of diagrams, that's the way it comes out. Okay, so now we can put h equal to 0. Okay. Now let's suppose that I want to compute. I am in a translationally invariant system, but I want to compute m of x1, m of x2. Okay, I want to compute this correlation function, but for magnetization at 2 different points. So the way to do this with this formalism is to introduce functional. So I'll tell you what the functional is in 1 minute. So here I get trace e to the minus beta k minus integral d cube x. I won't write the cube. H of x m of x. Okay. So we call this a functional because it takes a function h of x and it maps it into a scalar. Okay, that's the general definition of a functional. Now, if I want to, follow this scheme here, what I will do is I will take the functional derivative that I need to define in a minute of log of z of h with respect to beta h. Okay, so this delta here is a functional derivative, and that will give me, following this this scheme here, that will give me, here I need to specify x1, m of x1. Okay, how does that come about? It comes about from the definition of the functional derivative. So if I take the functional derivative with respect to h of x1 of the integral dx h of x m of x, this is equal to m of x1 if I define the functional derivative of h of x1 which and h of x as delta of x minus x1. So you see this? If I take this inside and I use this rule, I will get this. Okay, so this functional derivative is nothing but a generalization of partial derivatives, right? If I have two independent variables, let's say y I and y j, okay, y1, y2, y3, independent variables. So, and now I take a partial derivatives of dy1 with respect to y2. This is equal to delta ij, where delta now is a Kronecker delta. Okay. So you see, this is very easy. This is just a generalization to the continuum. But you see, the usefulness is this. Is I get this. So now, if I compute the second functional derivative of the z of h with respect to h of x1, h of x2, then this is equal to m of x1, m of x2 in the presence of the field, the h, minus m of x1 times m of x2, h. Now, if I want this at h equals 0, I just need to put h equals 0. Okay. Excuse me. So we will use now this exactly this approach for Green's functions. So this source field method was employed by Schwinger in the context of quantum electrodynamics, and Martin and Schwinger in the many-body problem. So at the same time, Feynman was working on Feynman diagrams in the context of quantum electrodynamics. So both of them, including Tomonaga in Japan, earned the Nobel Prize for quantum electrodynamics. But they were competitors and they had very different personalities. I mean, you know that Feynman was very flamboyant with showman, if you want. And Schwinger was really a genius, but much more less flamboyant, if you want. More of a very quiet guy. So they didn't like each other very much. So at Harvard, where Schwinger was, it was forbidden to draw Feynman diagrams. But Feynman diagrams are very useful to develop the intuition. So the story is that the students would go in the basement so that nobody saw them, and they drew Feynman diagrams. We were like drawing dirty pictures, if you want. So here we will use this Schwinger Martin approach to many-body problem because it is more easily generalizable to non-perturbative cases. I mean, to cases where perturbation theory is not the best thing to do. So, for example, dynamical mean field theory and certain theorems like, for example, the so-called Luttinger theorem that I already alluded to before are easier to prove it within this formalism. But the formalisms are equivalent. In the notes, you have both Feynman and Schwinger, but I cannot do both. I mean, there's no time to do both. It's useful to know both, but there's a finite amount of time, and I cannot do both approaches. On the other hand, we will get some algebraic equations. So because in the Schwinger approach there's a lot of algebraic equations, and we will also draw diagrams. They will not be Feynman diagrams in the sense that the rules to go from the diagrams to algebraic equations will be different, but still the diagrams will help to remind ourselves what we are doing and to know the physics of what's happening. So is that clear? Okay. So let's see how we can generate perturbation theory and some equations for the many-body problem using source fields. So again, I will have a functional of source phi that will be equal to a trace e to the minus beta k times the time-ordered product theta of the exponential of minus psi dagger 1 bar phi 1 bar 2 bar psi 2 bar. Okay, now I need to tell you what I mean by this. Okay, and you will see why I use this notation. So what is psi dagger 1 bar, phi 1 bar, 2 bar, psi 2 bar? That's equal to, the bar means that I need to integrate over and sum over everything in sight. So I will sum over spin indices, sigma 1, sigma 2. So these field operators have the spin indices, sigma 1, sigma 2. They are defined in space, so I have d cube x1. And there's some imaginary time dependence. So I have integral from 0 to beta theta 1. And then the same thing for 2. So I have the integral d cube x2, integral from 0 to beta d tau 2. And now I have so I'm continuing here. I have psi of sigma 1 x1 tau 1 dagger phi of x1 tau 1 x2 tau 2 times the psi of x2 tau 2. Okay. So you see why I use this notation, right? It's a mess to write the.
There's a sigma missing.
And there's a sigma 2 missing. Thank you. So in other words, what we mean by 1 one is x1, tau 1, sigma 1. Okay. And the bar means that I integrate over everything inside. You can think of this as matrix multiplication, right? A vector, matrix, vector. This is like a row vector, matrix, column vector. Okay. So it's useful to think of this this way.
Quick question. Does the source field does have a spin dependence or no?
Yes, yes. The source field, I forgot the spin dependence. Sigma 1, sigma 2. Thank you. Or usually we put it here, sigma 1, sigma 2. Okay. So now let's see what happens if I take the functional derivative of log of z of phi with respect to phi 2, 1. Okay. So if I take the functional derivative of this, I will get again 1 over z. And here I will get the trace of e to the minus beta k. Okay, and now I showed you earlier that when I have a time-ordered product, and here these are operators, but the phi here are just numbers. So if I take a derivative of a time-ordered product, it works just like an ordinary derivative. So the rule to differentiate the exponential is the same as for ordinary number, like in the classical case. Now, I need to tell you what we mean by delta of phi 1 bar, 2 bar, with respect to phi 2, 1. That's equal to delta of 1 bar 2 and delta of 2 bar 1. And what do I mean by delta? Sorry, all sorts of notation. Delta of 1 minus 2 is equal to delta real direct delta function, delta of x1 minus x2, delta of tau 1 minus tau 2, and delta of sigma 1, sigma 2, Kronecker delta. Is it okay? Now, this is when you need to ask your mathematician friend to go out of the room. Okay, because in this crazy notation, 1 can be equal to 2. You see? What it means when 1 equal to 2 is that you have two different variables, 1 and 2, but all the coordinates corresponding to these variables are equal. Okay, it's not that 1 is equal to 2, it's that the coordinates of 1 and the coordinates of 2 are equal. But this is the notation that's the convenient notation to use. Okay? No question, no objection, 1 equals 2. Okay. So now we have the exponential, we have this exponential. And then we've taken a derivative. So here we will have 1 bar equals 2. So I have psi dagger 2, psi 1, and I have a minus sign that comes from this minus sign. And now I will put this back in the order that we need for a Green's function. For a Green's function, we need psi1, psi 2. So I do psi1, psi 2. And we are in a time-ordered product, so with fermions, so that gives me another minus sign. So the final result, I will erase this.
Quick question. In
Yes.
the definition of our functional derivative with the delta function that we have at the bottom, do we need to sum at the bottom left for us? So the definition of the functional derivative that we have, do we need to sum over the coordinate 1 and the coordinate 2 in the both delta, or we don't need, because in the in our like exponential we sum over there?
Yeah, in the exponential we sum, and then when we take the functional derivative, it selects, 1 bar becomes equal to 2, and 2 bar becomes equal to 1.
Okay, so we just select them. We don't need to introduce a new sum.
Well, the thing is that there's an integral here.
Yeah.
So the derivative of the exponential is just the argument, and we need to differentiate the argument.
Okay.
Okay. So when we differentiate the argument, we use this. Okay, thank you for asking. It's confusing indeed. You have to use this. Okay. And because there's an integral here, the delta function, they just get rid of the integral and you just add this. Same thing as what we did in the classical case.
Okay, thank you.
Okay. Is that clear for everyone? Okay. Okay, so now what have I shown? I have shown that the functional derivative of log of z of this field phi with respect to phi 2, 1 is equal to minus, because for a Green's function, I need the minus. So there's minus g1, 2, and I will put some index phi here to remember that we still have this exponential. Okay. I can put phi equal to 0 now. I could do that. But let's not do it for now. So you see the labels here are inverted. I mean, this is just a question of definition, but it's a useful definition. So we'll keep it this way. So let me put the minus sign here. So this is the derivative of the g. Now, if I take the derivative of g, just like I did to find m of x1, m of x2, now I want to find higher order correlation function. Okay, so if I do delta g 1, 2, delta phi 3, 4, what happens? Okay, this is the g here. So when I differentiate with respect to the 3, 4, you will see that I will get a minus sign and a minus sign that cancel each other when I do the derivative. And using this rule for functional differentiation, I will have psi 1 psi dagger 2, psi dagger 3, psi 4, phi. Okay. So that is taking the derivative of this here. And using the fact that the derivative of an exponential is exponential times the derivative of the argument, and then using this. So that's the first term. And just like in the case of the magnetization, I have another term which comes from differentiating the denominator. Okay. So differentiating the denominator, what happens? I will write the answer and I will tell you why it comes out this way. G12 G43 of phi. Okay. So that was the G12 was this object. Now when I differentiate the denominator, I get minus 1 over z squared. I get another minus sign from this, and I get another minus sign from switching like this. So in the end, I get, with this minus sign, I have 4 minus signs, and it comes out with a plus. Okay, you can work it out to be sure, but that's the answer. Okay, and you understand why I have 4, 3 here, right? I took derivative with respect to 3, 4, but 3, 4 gives me psi dagger 3, psi 4. So for Green's function, it's the other side. So that's why I have G of 4, 3. So you see, we can, so this function of phi. So you see, we can get correlation. If we know this as a functional of phi, we can get these higher order correlation functions. Okay. So I will show you that in a little bit more detail right now, how this works. So this is where I do my cartoon here. Okay. You need to, you need to work out all the labels not to make mistake. You need to do everything correctly. But instead of being bogged down in labels and indices and everything, I will just do it, as I said, in a cartoonish way, just to show you what is the goal. I mean, where are we going with this? Why is that useful? Okay, up to now, everything I did did not depend on the value of on what the Hamiltonian is really. But now, let's see what happens if I compute the imaginary time derivative of psi of tau 1. Okay, I dropped the other labels for now just to simplify things. We know that this will give us, given the time evolution of these operators in imaginary time, this will give us the commutator of k with psi 1. So the quadratic part will give us another, would also be proportional to psi 1. So given this, I can write the equation of motion for the Green's function. In other words, if I write d tau 1 of the Green's function g of 1, 2 as a function of phi, what will happen? There will be a d tau 1 that will act on the theta function that come in the definition of the time ordering operator. Remember this? So there will be a a delta of tau 1 minus tau 2, a delta sigma 1, sigma 2, and delta x1 minus x2. Okay. So in our notation here, this is just 1. And now the dd tau 1 acts on the destruction operator here. Inside the definition of G, there's a psi 1. And the psi 1 obeys this. Okay. So the part that comes from the kinetic energy is usually put somewhere here. For example, we had in the case of non-interacting system, we had some psi of k. So what I will do is just write G0 minus 1. Okay. If there's only the kinetic term, so G0 minus 1 acts on this, so I will write it as G0 minus 1 of 1 bar if you want, and 1 bar here. So I can use delta functions. So in this matrix notation, if there was only the non-interacting part, I would get this. And that would all of these would be G0. But now I have some interactions. Okay. So let me drop these indices for now. So I have some interaction, and also I have the phi. So the phi will come in just like it does in the G0. So the phi will be here, and acting on G will be equal to 1, and then I get contributions that come from the interaction. And the interaction as V, and it has 4 field operators, right? It has psi dagger, psi, psi dagger, psi. But when you take the commutator with another psi, basically, in the end, it gets rid of a psi dagger. And this one also. In the homework, you are doing things like that, right? Just with the non-interacting case, but you can see that in the general case, that's what will happen also. So here I will have a psi dagger, psi, psi dagger, okay, when I take this. And then in the definition of G, I have a psi dagger that I put a derivative of psi, but in the G, there's a psi dagger that I just put, I mean, that's a psi, not a psi dagger. I got rid of one of the psi dagger. And now there's a psi dagger that I put to the right, right? The G contains a psi dagger. So I put psi dagger in. Fine.
I'm kind of lost. I don't know what we're trying to do right now.
I'm trying to show you what we're trying to do. I'm doing schematically what we will do with all the indices, and I want to show you that this is a way to generate perturbation theory. Okay. Now I have a definition for sigma. Okay, this is 1 plus sigma G, right? Because you see, this now takes the form G0 minus 1 minus phi minus sigma times G equals 1. Okay. So I have an explicit expression for sigma, which is this this thing. But these, whenever I have a correlation function with 4 fields like this, like I have here, I can obtain it from a derivative of G with respect to phi. Okay. So now I have an explicit expression for the self-energy. I have an explicit expression for the self-energy. I have that the sigma G is equal to this, which is a minus V, and this function is delta G delta phi minus GG. Okay, so sigma itself is just this times G minus 1. It's, yeah, just think of these as manipulating matrices all the time. So all of these have labels and they are just multiplied. Okay. Now, if I want to, so that's a very important equation, this one. And this one. So to compute the self-energy, I need an expression for this derivative. So let's find an expression for this derivative. Since G minus 1 is equal to the identity, it means that delta G delta phi times G minus 1 plus G times delta G minus 1 delta phi is equal to 0. So delta G delta phi is equal to minus, so I will write multiply by G minus 1, by G. So delta G delta phi multiplied by G here is minus G delta G minus 1 delta phi times G. Okay, so why is this useful? This is useful because I know G minus 1. G minus 1 is this. Okay. So when I take the derivative, functional derivative of G minus 1 with respect to phi, I get the first term that comes from this. So I get G delta phi G. And I have another term which comes from this. So I have plus G delta sigma delta phi times G. Now sigma depends on phi only through this, only through the Green's function itself. So that's perturbation theory. I mean, sigma depends on G. So it does not have any explicit phi dependence. So this I can write as delta sigma delta G delta phi, and I add times G. Now you see I have delta G delta phi that comes on both sides. So in the non-interacting case, I would have just this. But now it comes on both sides. So these are called the vertex corrections. And this one is called an irreducible vertex. So it looks, I mean, this guy here looks like a self-energy, but for a 4-point function. And delta G delta phi was 4 operators. And delta sigma delta G looks like a self-energy for this 4-point function, delta G delta phi. In other words, I have an integral equation for this quantity. So for example, you see you can evaluate here, if you want, you can evaluate this to lowest order, right? Like this. And then you have an expression for sigma that you can put, that depends on G, that you can put back here. And then you have an expression for delta G, delta phi. Okay, so these expressions are exact, but you can use them iteratively to build the perturbation theory. So you see, for example, if I substitute this here, I get for the self-energy sigma equals minus V times delta G, delta phi is this. So I have G, delta phi, and this G and the G minus 1, the G minus 1 gets rid of this G. Then I have minus GG. And and then I have this term as well. So the G minus 1 gets rid of this term, of this G. So I have plus G delta sigma delta G delta G delta phi. So you see sigma is already first order in potential. So if I want the leading order in V, I just drop this term because it has sigma here. Okay, that's the R3-Fock approximation. This I got rid of a G here. Okay, I have GG, but G minus 1. Okay. So that's the R3-Fock approximation. And I can also include, and you can generate perturbation theory that way, or you can do things non-perturbatively, like we will do. So that gives you an idea of what we will do. So the way we will proceed for the electron gas, and I will put back all the indices so that we know what we're doing. But this is just an overview of how things work out. So what we will do for the electron gas is we will just first take this R3-Fock approximation for sigma, okay, which is as if there was, I mean, it's sort of the lowest order in V. Then we will, the functional derivative of sigma with respect to G is easy, right? Because the G is there. So we will put that here. And this expression, delta G, delta phi, called delta G, delta phi, GG, can be used to compute the charge fluctuations. And that will give us the random phase approximation. And now that we have an approximation for delta G, delta phi, this random phase approximation, which will give us screening, plasma oscillations, and so on. So all things that can be measured, for example, with electron energy loss spectroscopy, I will comment on this. So once we have this RPA expression, this expression for delta G, delta phi, you see we can put it back here and get a better estimate for sigma. And that will be the GW approximation. Okay, so that's the whole roadmap. So everything is based on having G minus 1 here with this source field phi. And notice that even if the system is translationally invariant, for this formalism to work out, you have to have some phi that breaks all these symmetries. And at the end, we put phi equal to 0. So at the end, the expressions that we have are translationally invariant. But to derive the expression, we need to break all this translation invariance. Have a phi that depends on 1 and 2. So like Beta was saying, these are exact results. This, so this, and this are exact result. This as well. All I have done is use this expression for delta G, delta phi here. So all of these are exact expressions. This one we will not really need. So like Beta was saying, they are exact, so they are useless. So, because, I mean, you cannot solve all of this. You have to do iterative approaches, but the objects are well identified. We have the generalization of the self-energy here for charge fluctuations. You know, these are psi dagger psi, so we can have charge fluctuations here. And we have the generalization of the self-energy for these things. In other words, this object here will be a susceptibility, just like we described earlier in this class. And this susceptibility will have the form, if you want, chi0 over 1 minus v chi0. So it will turn out that this if I start from R3 here, this interaction vertex is just a v. So that's the RPA approximation. And chi0, what is chi0? Chi0 is just this guy. So this is G times G. So this will be called the Lindard function. So you see you have G times G, or the Lindard function again. And you put this, all of this on the left-hand side, and you get it in this, this form. Okay, so that's the roadmap, if you want. Because you see, already that's confusing. So when I put all the indices, then you have no idea where I'm going. Okay, but I will put all the indices, and we will do things carefully, and it will take some time. But the idea and the way to proceed in the end is very simple. So we have an expression for the self-energy that involves here the charge fluctuations. So in other words, the medium is polarizable. That's what gives you the GW approximation. So the self-energy depends on the charge fluctuations. And the charge fluctuations themselves depend on the functional derivative of the self-energy with respect to G. And these are, if you want, interaction vertices or irreducible vertices. I will explain what that is later. And once we have the charge fluctuations, we can put them back here. So they're sort of an iterative procedures. And we will start by this thing. So we'll use the simplest approximation for sigma, and then use it here to get the charge fluctuations from this. It will have this RPA structure. So the V is just delta sigma delta G in this approximation. But with this formalism, that applies as well for the Hubbard model, for any model that has a 4 fermion operator. And you can, and that's what we will do in two-particle self-consistent approach, you can do approximation for these vertices that can be in turn determined self-consistently. So that's why it's a powerful formalism. But so that's all there is. There is the expression for G minus 1, the expression for the self-energy that involves the charge fluctuations, because there are 4 fermion. You see, sigma involves 4 fermions, so it's density. So it has the charge fluctuations, and the charge fluctuations themselves can be obtained from this if sigma is obtained from functional derivative of this. So we can do simple approximations for this, put there, get the charge fluctuations. In other words, we get the charge fluctuations as if we had some non-interacting particles in some way. And then we need to go one step further to improve the self-energy. Does it sound clear? Is it becoming clearer now?
Yeah.
So you see the use of the phi. Why did we have this phi? We had the phi just to derive these equations. And now we put phi equal to 0 at the end. Okay. But I will need to redo all of this with all the indices, and these will all be matrix multiplications. So I will do all of this with putting all the indices back. And so it will be a little bit painful, but we will get to this relatively quickly. Okay. Okay, so see you on Wednesday. If you have questions, I will stay again to answer your questions.